Right. So let's do free body and solve. So we have this one whereby we have a mass of 7 kg, an applied force of 80 newtons to the left, a frictional force of 16 newtons. We are going to be solving for acceleration there. And then let's draw first the free body diagram. We have the gravitational force acting downwards, the normal force that is perpendicular to the surface there. We are going to be having the applied force acting to the left-hand side there. And then the only applied force acting there acts to the left. That means that our object is going to accelerate to the left-hand side, and therefore the frictional force here is going to oppose the motion towards the right-hand side there. And then now, the next thing that we do, our object goes to the left-hand side, so we are going to choose to the left as positive. That means that our applied force is going to be positive, and therefore our frictional force is going to be negative there. Then Newton's second law, the net force is equal to the mass multiplied by the acceleration. We are going to have our positive applied force minus our negative frictional force equal to mass multiplied by acceleration. What we have here is 80 minus 60, giving equal to our mass of 7 multiplied by the acceleration that we want to calculate. 80 minus 16 will give us a 64 equal to 7a to solve. Divide by 7 here to cancel. Divide by 7 also on the left hand side. And our acceleration is going to be 64 divided by 7, we get 9.14. We get 9.14 meters per second squared. Our answer is positive. We refer back to our choice of direction. We choose left as positive, and therefore our answer is going to be to the left hand side there. With this one, we have a mass of 8 kg, a coefficient of 0.2, an applied force of 70 newtons to the right hand side there. Now let me just change the coefficient over there to 0.4 there. So let's have a coefficient of 0.4, an applied force of 70 newtons. We are going to again calculate the acceleration there. And now let's start with the free body diagram. We are going to be having there the gravitational force. We are going to be having the normal force there. And then we're going to be having an applied force acting towards the right-hand side there. And because we only have one applied force acting to the right-hand side, the object is going to accelerate to the right, and therefore the friction is going to be to the left there. Kinetic friction there is going to be to the left-hand side there. And that's our free body diagram then. And in this case, we don't have frictional force. We are given the coefficient, so we must calculate the frictional force. Now, in order to find the frictional force, we must first find the normal force. And for that, we focus on the vertically acting forces there. What we see there is that the normal force is balanced with the gravitational force there, because our object does not move vertically there. So the normal force is equal to the gravitational force. We know that the gravitational force is mass multiplied by gravitational acceleration there. So we're going to be having 8 multiplied by our 9.8 there. And what we're going to be getting here is 8 multiplied by 9.8. What we get here is 78.4 newtons. And then we say that the kinetic friction is equal to the coefficient of kinetic friction multiplied by the normal force. So we have a coefficient over there of 0.4 multiplied by the normal force. We have just calculated it. We found it as 78.4 there. Now let's multiply our 78.4 by 0.4. And let's see what we get here. We get that 1.38 there of frictional force there. So we calculated our normal force first, and then we got our frictional force afterwards there. And then the next thing that we do here is that we say that our only applied force is applied to the right. The object accelerates to the right. Therefore, we are going to choose to the right as positive there. So that means if we focus horizontally, our applied force is going to be positive to the right, and our frictional force that is to the left is going to be negative there. So Newton's second law, the net force is equal to the mass multiplied by acceleration. So what we have under net force here, we have the applied force minus the frictional force that is negative equal to the mass multiplied by acceleration here. Now let's substitute. Our applied force is 70 minus our friction is that 1.38 is equal to our mass is 8. Let's solve for acceleration there. And then what we have here is 70 minus that 1.38 giving us a 38.62 here. So we have a 38.62 here is equal to 8a. To solve for acceleration, we divide by 8. We divide by 8 over there as well. So the 8 is going to cancel over here. So we have a 38.8, 38.62 divided by 8. This gives us an acceleration of 4,83 meters per second squared. We refer back to our choice of direction. We choose right as positive. Our answer is positive. Therefore, our answer is to the right hand side. For this one, we have an applied force of 55 newtons acting on a 6 kg block at an angle of 30 degrees with the horizontal there. We are again going to solve for acceleration. The coefficient of friction is 0,3 here. So that means we have to calculate the frictional force. But before that, we have to calculate the normal force then. And let me also say that try to solve the problem first, so that the calculation is more like corrections there. All right, so let's have our free body. So what we have here is we have the gravitational force. We have the normal force perpendicular to the surface, and then we have a force that is acting horizontally to the left hand side. So in the x direction, our force is towards the left hand side, and vertically in the y, our force is acting vertically upwards there, Fy there. It is acting vertically upwards there. And then once again, our object there accelerates to the left hand side. Therefore, the frictional force is going to act towards the right hand side, as it will oppose the motion by definition there. All right, so once we are done with our free body diagram, the next thing to do is to calculate the normal force. To do that, we consider the vertically acting forces. What we have there is we can see that the vertical component and the normal force are balanced with the gravitational force, since our object is not moving vertically. So it means that if you add the normal force with the vertical component, they must equal to the gravitational force, because they are balanced with the gravitational force. Now transpose the vertical component over to that side. What we have there is the normal force is equal to the gravitational force minus the vertical component there. Now what we have, gravitational force is mg, and the vertical component is f sine theta there. So our mass there is 6, g is 9,8. Our force is 55, multiplied by the sine of our angle there is 30 degrees there. So on our calculator, what we have is 6 multiplied by 9,8. What we have here, what we get there is 58.8 minus 55 multiplied by sine 30 degrees, giving us here a 27.5 there. Now 58.8 minus 27.5 gives us a 31.3 newtons there, and that is how we calculated normal force in this situation there. Now it changes because this force acting at an angle influences the normal force, because it lifts the box there a little bit there. It lifts our object a little bit there. And then now the frictional force is equal to the coefficient multiplied by the normal force. Our coefficient is 0,3 multiplied by the normal force that we have just calculated. It's that 1.3, close bracket there. So what we're going to be having here is 0,3 multiplied by that 1.3 there, giving us a 9.39 newtons there. So now that we have calculated our frictional force, now it's time to go to our Newton's second law equation there. But before we do that, we said that our object is going to accelerate to the left hand side. So we are going to choose to the left as positive, assign this direction to our horizontally acting forces. That means that our horizontal component that is to the left will be positive, and the frictional force that is to the right is going to be a negative there. And then what we have here is net force is equal to mass multiplied by acceleration. Looking at the free body diagram, the horizontally acting forces there, we have our horizontal component there minus the frictional force there being equal to the mass multiplied by the acceleration there. So let me split that a little bit there. So what we must do further is that we must find the horizontal component there, our fx. Our fx, the horizontal component, is equal to our force multiplied by cos theta there, squeezed up a little bit there. So what we have basically there is we have the 55 multiplied by cos 30 degrees there, giving us a 55 cos 30 there, is 47.63 there. So we have our horizontal component as 47.63 there. By the way, our horizontal component, our vertical component is the force multiplied by sine theta. Our horizontal component is the force multiplied by cos theta there. So we had 55 multiplied by cos 30 degrees, and it gave us 47.63 there. So that means here we are not going to be substituting the 55 as it is. We have to first multiply it by the cos of the angle with the horizontal, so that we can get our horizontal component there. So here we substitute 47.63 minus the frictional force that we have calculated. With this one, we have an applied force of 80 newtons there. That's 80 there. Looks like a 90. It's a 90 just fixed up a little bit there. So that's an 80 newtons of applied force acting at an angle of 40 degrees to the horizontal on an object of 12 kilograms mass. We are going again to solve for acceleration there, and you can see already there we have the coefficient of frictional force. So that means we are going to be solving, we're going to first be calculating the frictional force. And remember, to do that, we must first calculate the normal force there. So we are going to refer to our free body diagram for that calculation there. So let's start first by drawing our free body diagram there. So we have our gravitational force acting downwards, and then perpendicular to the surface we have the normal force there, and then only applied force is acting towards the right hand side. That means that the frictional force is going to be to the left hand side there. It's acting horizontally to the right hand side there, if I say it correctly. And then our force acts horizontally to the right hand side there, and it acts vertically downwards there. Horizontally to the right hand side, but vertically our force acts downwards there. In the y direction, it acts downwards there. So that is our free body diagram for this case there. So after we draw our free body diagram, the next thing that we do there is we look at our free body diagram in the vertical dimension. What we see there is that the gravitational force and the vertical component balance with the normal force there. So so the normal force then is balanced with the gravitational force and the vertical component there. So the normal force is equal to gravitational force plus the vertical component there. That means that they are balanced there. The gravitational force there is mg, as we know, plus the force multiplied by sine theta there. Our mass there is 12 multiplied by g is 9.8 plus our force there is 80 multiplied by sine of 40 degrees there. So what we're going to be having here, we have 12 multiplied by 9.8 there, giving us a 117.6 plus 80 sine 40 gives us a 51.42 there, 51.42 there. So we're going to say 117.6 plus 51.42, it gives us a 169.02 there, 0.02 newtons there. So to calculate the frictional force, we're going to say that kinetic friction is equals to the coefficient multiplied by the normal force that we have just calculated. Our coefficient is 0.1, and our normal force, we found it as 169.02 there. And then what we're going to get here is a 16.902 newtons there as our frictional force there. And then what we must do is that we must calculate our horizontal component there, the fx there. So for that, we're going to say that fx is equal to our force multiplied by cos theta. This is going to be our force of 80 multiplied by cos 40 degrees there. And then our answer is going to be 80 multiplied by cos 40. It gives us a 61.28 there. So what we get here, 61.28 newtons there for our horizontal component fx there. Now our object is going to accelerate to the right hand side, so we are going to choose to the right hand side to be positive. That means our horizontal component fx is going to be positive, and the frictional force to the left there is going to be negative there. So what we are going to have here, Newton's second law, net force is equal to the mass multiplied by the acceleration. And under the net force, we are going to be looking at our free body diagram in the horizontal dimension. What we have is a positive horizontal component minus the negative frictional force that is to the left is equal to the mass multiplied by the acceleration there. So what we have there is 61.28 minus 16.902 being our friction that we have just calculated now is equal to the mass of 12 multiplied by the acceleration, which is what we are trying to calculate then. So just to simplify a little bit over here, we have 61.28 minus 16.902 giving us a 44.378 is equal to 12a there. Divide by 12, and our acceleration there, we have 3.698 there. I'm gonna write it as that, 3.698 meters per second squared there. We will refer again to our choice of direction. We chose to the right as positive. Our answer came out as positive, and therefore our acceleration will be to the right there. All right. Right, with this one we have an unknown force, an acceleration of 2 meters per second squared to the right there, and a frictional force there of 12 newtons there. The force is acting at an angle of 50 degrees, the horizontal, on a block of mass 10 kilograms there. So let's draw a free body diagram there. We have the gravitational force. We have the normal force there, because our object is still on the surface. So to break down our applied force, it is acting horizontally to the right hand side, and it is acting also vertically downwards there at the same time there. Now our only applied force is acting to the right, therefore the frictional force will oppose to the left hand side there. All right, and then now we have an acceleration of 2 meters per second squared there. So what we're going to do here is that we're going to choose to the right as positive there, because our object accelerates to the right. So to assign that direction there, we are going to choose to the right as positive and assign that direction there to our horizontally acting forces. So the horizontal component will be positive to the right, and the frictional force that is to the left is going to be negative there. And then our horizontal component there will be the force there. It's unknown, multiplied by cos theta. Our force is unknown, multiplied by cos 50 degrees there. So we'll write it as it is there. So we say then a net force is equal to mass multiplied by acceleration. What we have, according to our free body diagram, if you focus on the horizontal acting forces, so we have our horizontal component of the applied force minus the frictional force is equal to the mass multiplied by the acceleration there. And then we substitute it directly as the force, the unknown force, multiplied by cos 50 degrees minus our frictional force of 12 is equal to our mass of 10 and our acceleration of positive 2 to the right there. So what we're going to be having here is we're going to be having force cos 50 degrees minus 12 is equal to 10 times 2 is 20. Now let's transpose the 12 over to that side. We're going to be having a f cos 50 there, f cos 50 there, and I've just been alarmed of something very quickly. Let me just change my acceleration there a little bit there. Let me change it to 3 there, so that it's not similar to an upcoming question. So let me have an acceleration of 3 instead there. So that's going to be 30 there. So let me transpose the 12 over to that side there. So I'm going to be having 30 plus 12. This will give me a 42. So the f cos 50 degrees on this side here. And to solve for the force, we're going to divide by cos 50 degrees. Divide by cos 50 degrees there. And our force is going to be 42 divided by cos 50 degrees here, giving us a 65.34 newtons there, 65.34. With this one, we have an unknown mass accelerating at 4 meters per second squared. An applied force of 75 newtons applied at an angle of 30 degrees to the horizontal there, and a coefficient of friction of 0.2 there. So we are going to be calculating the mass there. So let's draw our free body diagram. So we are going to be having the gravitational force acting downwards, the normal force acting upwards there, and then we are going to have our force is acting horizontally to the right hand side there, and it is at the same time acting vertically upwards there, Then our only applied force acting to the right hand side means that the frictional force is going to oppose the motion and act to the left hand side there. Now in order to calculate because we have coefficient, in order to calculate the frictional force, we need to first calculate the normal force. So we are going to be focused on the vertically acting forces. You can see there that the normal force there with the normal force plus with the vertical component there are balanced with the gravitational force there. So the upward acting forces are balanced with the downward acting force. We transpose the vertical component over to the right hand side. So we have the normal force equal to the gravitational force there minus the vertical component there. And then we know that the gravitational force there is mg, and the vertical component there is the force multiplied by the sine of theta there. So what we're going to be having here, we have our unknown mass multiplied by 9,8 minus 75 multiplied by sine, oopsie there. So before we substitute is sine theta, and when we substitute now, we have sine 13, excuse me for that. And what we're going to be having here is m multiplied by 9,8. Let's just rearrange that to 9,8 multiplied to m minus a 75 multiplied by sine 30. So we have 75 sine 30 degrees, giving us a 37.5 there. So we have normal force as 9,8 m minus 37.5. It is in terms of the mass. And then the next thing that we do, we calculate the frictional force there. So the kinetic frictional force is equal to the coefficient multiplied by the normal force there. So what we're going to be having here is our coefficient of 0,2 there multiplied by, let's substitute there, let us move it a little bit there. Let's have it moved a little bit there. Before that, let's have our coefficient changed a little bit there to 0,3 there, so that's not similar to an upcoming question there. So what we have there is the kinetic friction is the coefficient of friction multiplied by the normal force. So we're going to be having 0,3 multiplied by 9,8 m minus 37.5 there. So we are going to multiply by 0,3 here and here inside of the bracket. So what we are going to be having is 0,3 multiplied by 9,8, giving us a 2,94 there. What we have here is 2,94 with the m minus 0,3 now multiplied by 37.5 there, giving us 11.25 there. So we have 11.25 there. So here is the frictional force, and it is in terms of m there. So the next thing that we do is that we are going to choose a positive direction. We are going to choose the right as positive, as our object is accelerating to the right hand side. So our horizontally to the right force, the horizontal component there is going to be positive to the right, and our frictional force there is going to be to the left there. It's going to be to the left, and therefore it will be negative there. Right. So the next thing that we do here, Newton's second law, the net force is equal to mass multiplied by acceleration there. We have under net force the positive horizontal component minus Fk frictional force there. Fix that a little bit. Put that in view. Equals to mass multiplied by acceleration there. So what we're going to be having here But before we substitute here, we still have to calculate what the horizontal component is. So we have horizontal component Fx is equal to the force multiplied by cos theta. Our force is 75 multiplied by cos 30, and therefore it's going to be 75 cos 30 gives us a 64.95 there. So our horizontal component is 64.95 newtons there. So we're going to be having here 64.95 minus our frictional force is this. So it's in a bracket 2,94. A bracket because it is 2 terms here. So we must substitute it inside of a bracket there. So what we're going to be having here is 2,94 multiplied to that m minus the 11,25 is equal to our mass here, it's unknown, multiplied by an acceleration of 4 there. So to simplify here, we're going to be having 64.95. The positive multiplied by negative there. We multiply inside of the bracket by this negative. So positive times negative there is negative 2,94 with the m. And then here we say negative times negative is positive. Plus 11.25 is equal to 4 times m there is simply rearrange there and get 4m there. And then what we're going to do next is that we're going to transpose the 2,94 over to the right hand side there. So we are going to be left with 64.95 on the left hand side plus 11.25 there equal to, on the right hand side we are going to be having the 4m, and then the 2,94 goes over to the right hand side. Let's keep our m rate. 2,94m goes over to the right hand side and becomes positive on that side there. So 2,94 there with the m there. So what we have on the left hand side, we have 64.95 plus 11.25 giving us here a 76.2. So here we have 76.2 is equal to 4 plus 2,94 on the right hand side there. It gives us a 6,94 there. So we have 6,94 multiplied to m. So we're going to divide on both sides by 6,94 and divide by 6,94. 6,94 is going to cancel over here, and our mass is going to be, let's write it over here on the calculator. We have 76.2 divided by 6,94, and this gives us a 10.98 there. So we have our mass as 10.98 kilograms there, right there. Right, so what we have with this one is we have 2 applied forces. An applied force by, let's call this a force applied by Lebu of 100 newtons to the right, and a force applied by Neo to the left hand side of 65 newtons there to the left there. Lebu's force acts at an angle of 30 degrees to the horizontal, and the coefficient of friction is 0.4 there. So that means once again that we're going to have to calculate the frictional force there because we have the coefficient. So that also means that we are going to calculate the normal force as well there. So let's start with the free body diagram. So our free body diagram is going to be, we have the gravitational force, we have the normal force there, and we have Lebu's horizontal component there to the right hand side there, and we have Lebu's vertical component there upwards there, and then we have the force applied by Neo there. We have the force applied by Neo there to the left hand side there. So when it comes to this question here, when you have 2 applied forces, it's important to, before you draw the friction there, we must first determine it there. To determine the frictional force, we need to first determine the direction of motion, and that means we need to check between Lebu and Neo which force is bigger horizontally there. So that means that we should go right ahead and calculate the horizontal component of Lebu's force there. So we're going to say Fx is equal to the force multiplied by cos theta. So what we have here is 100 multiplied by cos 30 there. And then what we're going to have here is 100 cos 30 there, giving us an 86.6 newtons there. So the point here is this, is that if our object accelerates to the right, the friction is to the left. If the object accelerates to the left, the friction is to the right. So in order to determine in what direction will our object accelerate, we need to check which one of these horizontally acting forces is bigger. So you can see that the horizontal component of Lebu, we must first calculate the horizontal component of the force system. So F neo is already horizontal. So the horizontal component that we need to calculate is the horizontal component of Lebu, and we find it to be 86.6. So that means that the object is going to accelerate to the right because the bigger horizontal force is the horizontal component there of Lebu there. So that means that if we calculated the horizontal component and we found out that it was smaller than the 65, then the object will have to accelerate to the left hand side, and the friction will have to be to the right hand side. But in this case, we found that the horizontal component of Lebu's force is bigger than Neo's horizontal force, and therefore the object is going to accelerate to the right, and that means that the frictional force is going to be towards the left hand side there, towards Neo's side there. And that's the determination that we have to do before we assign a direction to our frictional force there. All right, so the next thing that we're going to do here is that we are going to calculate our normal force as usual. So again, we have the normal force and the vertical component balanced with the gravitational force. So what we have there is the normal force there with the vertical component balanced with the gravitational force. So we transpose the vertical component over to that side. We have the normal force equal to the gravitational force minus the vertical component. So what we have here is mg minus the force sine theta. So we are going to have 7 multiplied by 9.8 minus our force there. So which force? Are we taking Neo's force or Lebu's force? Remember, the vertical component is Lebu's vertical component there. It is the one that is acting at an angle here, and therefore influencing the normal force there. So we're going to be having the 100 multiplied by the sine of 30 degrees there. So that's 30 degrees there, a little bit over there, on that there. And then we're going to be having here, so what we have, let's write this again, minus 100 sine 30, just to put it in view there. So what we have here is 7 multiplied by 9.8 is equal to 68.6 minus 100 sine 30. 100 multiplied by sine 30 degrees, it gives us a 50. 68.6 minus 50 will give us an 18.6 newtons there of normal force there. And then now the frictional force is the coefficient multiplied by the normal force. So we're going to be having our coefficient of 0.4 multiplied by 18.6 there. So 18.6 multiplied by 0.4 gives us a 7.44 there. So our frictional force is 7.44 newtons there. So when it comes to a problem like this, whereby you have two applied forces, in usual cases, is that if you have an applied force at an angle, we are going to take that force and use it to calculate the normal force there. At the point whereby we're going to find the vertical component there. So in this case, it becomes a question of which applied force are we going to use to calculate the vertical component there. We use the force that is acting at an angle there. So that is the one that is influencing the normal force there. That is the one that has a vertical and a horizontal component there. All right. So once we have the frictional force as well as the vertical component there, it's time to do Newton's second law. So Newton's second law, the net force is equal to the mass multiplied by the acceleration there. So for our net force there, Once again, we have already determined that our object is going to accelerate to the right hand side. So we are going to choose to the right as positive there, and then say that this horizontal component fx there is going to be positive. The force of Neo to the left hand side will be negative, as well as the frictional force to the left hand side therefore will be negative there. So what we are going to have in this case under the normal force here, under the net force, is going to be the horizontal component there of label minus the force of Neo minus the frictional force is equal to the mass multiplied by the acceleration there. So we're going to be having, let's substitute here, we're going to have the 86 there, 0.6 minus Neo's force of 65 there, minus the frictional force we got as 7.44 is equal to the mass of 7 multiplied by the acceleration, which is what we're trying to calculate here. So let's simplify here. 86.6 minus 65 minus 7.44 is equal to 11.46 there, 14.16 rather is 14.16 is equal to 7a divided by 7 divided by 7. Our acceleration there will be equal to 2.02 there, 2.02 meters per second squared. And we have 10 kg body A as well as 15 kg body B, and the coefficient of friction for A is 0.2 and the coefficient of friction for B is 0.3 there. And an applied force of 80 newtons is applied on body B at an angle of 30 degrees with the horizontal there. So what we want to do ultimately is that we want to calculate the acceleration of the system as well as calculate the tension there. But before we get to that part, we must do a couple of things, including drawing free body diagrams for both bodies, calculating the frictional force for both bodies there. So let's start by drawing the free body diagram for body A. So what we're going to have is we're going to have the gravitational force acting downwards there. And then perpendicular to the surface here, we are going to be having the normal force over there. And then how we deal with frictional force is that we say the only applied force acting on our system is acting towards the right hand side. So it is safe to assume that our bodies are going to accelerate to the right hand side. Therefore, the frictional force, by definition being the force that opposes the motion, will oppose the motion and therefore act towards the left hand side. And then we have kinetic frictional force there acting towards the left hand side. And for the tension force is that we're going to break the string here, the rope over here, and you can see that the string pulls body A towards the right hand side there. So the tension force for body A is towards the right hand side there, Ft there. Let me scale it up a little bit more correctly there, that the tension force is greater than the frictional force there. And obviously for body B, we can already see that the string pulls body B towards the left hand side there. So that means the tension for B is going to be towards the left hand side there, like that there. And we can also already see that both of these tension forces over here are of equal magnitudes there, but we can see that they are in opposite directions. But it's also true that they are of equal magnitudes there, and they are therefore an example of Newton's third law action-reaction pairs there. And then we also have the gravitational force, of course, for body B, as well as the normal force there, perpendicular to the surface. And then using the very same reasoning there, our bodies are going to be accelerating towards the right-hand side, and therefore the frictional force, even for B, will be towards the left-hand side there. The frictional force will be towards the left-hand side there. And then in dealing with the force, the applied force acting at an angle over here, our force is basically acting towards the right-hand side there, horizontally towards the right, but then vertically acting upwards there. So what we have for our applied force there, we have it horizontally towards the right-hand side there in the X direction, and then we have it vertically in the Y direction acting upwards there. And these are our free body diagrams there. Now, our free body diagrams are going to help us in calculating the frictional forces. So for body A, what we have here, we can see, because our objects are not accelerating vertically, they're not moving vertically, not accelerating vertically. So that means that the vertical forces are balanced. So let's start with body A. That means that the normal force there is balanced with the gravitational force over here. These two are balanced. And then therefore the normal force is equal to the gravitational force, which is equal to mg. Now our mass is 10 and g is 9,8. This will give us a 98 newtons there. And that's the normal force calculation for body A. Now let's do normal force calculation for body B. So for body B, you can see that the upward acting forces there are balanced with the downward acting force there. So that means that if you add the normal force there to the vertical component there, they must be balancing with the gravitational force there. So that means that if you transpose the vertical component there, we are going to be having the normal force being equal to the gravitational force minus the vertical component over there. So the gravitational force is mg, the vertical component is the applied force, multiplied by the sine of the angle there with the horizontal there. So what we'll be having on this side is 15 multiplied by 9,8 minus our applied force of 80 multiplied by the sine of 30 degrees then. So let me break these apart a little bit over there. So what we'll be having on the side there is 15 multiplied by 9,8 is going to give us a 147 there, minus 80 sine 30 giving us a 40 over there. And then 147 minus 40 is 107 newtons there. Now once we have both normal forces, it is now time to calculate the frictional forces there. So I'm going to be having the kinetic frictional force for A will be the coefficient of kinetic frictional force multiplied by the normal force. So what we have for coefficient is 0,2, and the normal force was calculated and found as 98 there. And then we put this in our calculator. We have 0,2 multiplied by 98 there, giving us a 19.6 there. So the frictional force for body A is 19.6 there. So what we have here for A, for friction, we have 19.6 newtons there. And then for B, again, the kinetic friction is equal to the coefficient of kinetic friction multiplied by the normal force. So it's going to be 0,3 multiplied by the 107 that we have just calculated there. We're going to put this in our calculator. So it's 0,3 multiplied by 107 there. And this gives us a 32,1 there. So the friction for body B is 32,1 newtons over there. So we have now calculated the frictional force for body A and body B. And the next thing to do here, once we have our frictional forces, the next thing for body A and body B, and the next thing to do here, once we have our frictional forces, the next thing to do here is to choose direction there. So we choose direction of motion as positive there. So our objects are going to be accelerating towards the right hand side, so we're going to choose to the right as positive there, and then only focusing on the forces that are acting in the horizontal dimension, because our objects are moving horizontally. So the horizontal component, the Fx, acting towards the right hand side will be positive, and the frictional force, this frictional force there, will be negative towards the left hand side, and this tension force that is towards the left hand side again will be negative then. But this tension that is towards the right hand side will be positive, and this friction acting towards the left hand side will be negative there. And then while we're still doing that, let us calculate the horizontal component there. Fx is the force multiplied by cos theta. So we're going to be having the 80 multiplied by the cos 30 degrees there, and then what we have is 80 multiplied by cos 30, and this gives us a 69.28 there. So we get here 69.28 newtons there as our horizontal component there, Fx there. Now the Newton's second law says that the net force is equal to the mass multiplied by the acceleration. Let's write this on both sides. Let's have this for both bodies over here. The net force is equal to the mass multiplied by the acceleration there. And according to this free body diagram here, the net force is the tension minus the friction there, that is negative here. And then we have this equals to the mass multiplied by the acceleration. And then for this free body diagram, we have the horizontal component Fx as the positive one, minus the tension there because it's negative to the left, minus the frictional force because it's also negative to the left, is equals to mass multiplied by the acceleration over there. Okay, and then now let's substitute what we have. We don't have the tension, so we write Ft there. Minus the friction, we calculated it as 19.6 is equals to the mass. The mass here is 10 for body A, multiplied by the acceleration, which we don't have there. So let's make the tension the subject of the formula by transposing this 19.6 over here. So we're going to be having the tension equals to 10A plus 19.6 here. This 19.6 jumps over to that side there and becomes positive there. So let's call this equation 1 there. And then for this one, our horizontal component Fx is 69.28 minus the tension force we don't have, minus 32.1 is equals to our mass of 15 multiplied by the acceleration A that we also do not have there. Then let's simplify over here by saying 69.28 minus the 32.1, and this gives us a 37.18 minus the tension is equals to 15A there. And let's call this one equation 2 then. So we have equation 1 and equation 2. So the next thing that we're going to do here is that we're going to substitute equation 1 into equation 2 here. What does this mean? It means that because here we have tension as the subject of the formula, so where we see tension here on equation 2, we are going to be putting this 10A plus 19.6 here. So we're going to be having 37.18 minus into open bracket 10A. We are substituting something that has two terms, so we must put it in a bracket there, and then close the bracket is equals to 15A there. Now let's simplify. 37.18 positive here, you see here, positive multiplied by negative over here, we're going to be having negative 10A. Once again, inside of the bracket, this positive multiplied by the negative there is negative minus 19.6 there is equal to the 15A over there. To correct the like terms, we are going to transpose this 10A over to that side there, and then on this side we are going to be left with 37.18 minus 19.6 is equals to 15. The 10 jumps over to that side and becomes positive on this side here. So we already over here we have 15 plus 10 giving us a 25A there, and here we have 7.18 minus 19.6, and this gives us a 17.58 here. Then we're going to divide here by 25, divide here by 25 here, and then we have here acceleration as 0.703 meters per second squared towards the right hand side there. And then in order to calculate the tension, we are going to take our equation 1 and say Ft is equals to 10A plus 19.6 here, plus 19.6 over there, and this is going to be 10 multiplied by 0.703 plus 19.6. We put this in our calculator. We have it's going to give us 26.63 newtons there of tension. All right. In this scenario here, we have a system accelerating to the right hand side at 2 meters per second squared, an applied force acting on body B of an unknown mass, an applied force of 90 newtons acting at 40 degrees to the horizontal there. The body A has 7 kg, and the coefficient of friction for A is 0.4, and the coefficient of friction here is 0.2 here. So what we want to do here is that we want to calculate the mass of body B, and to do that we are first going to draw free body diagrams, calculate frictional forces there, and then calculate the mass there. So to start with, let's draw the free body diagram for body A. The free body diagram for body A is going to be, we have our dot over here, we have the gravitational force acting downwards, and then we have the normal force from the surface that is perpendicular to the surface. And to deal with the normal force, we say that our objects are going to be moving towards the right hand side. Therefore, friction will oppose that towards the left hand side there. And we're going to have our kinetic friction towards the left hand side there. To deal with the tension forces, we are going to say, let's break the rope here. What we see here is the rope pulls body A towards the right hand side there. So we're going to be having the tension towards the right for A there. And that's the free body diagram for A. Now for B, we're going to be having the gravitational force downwards, and then we're going to be having the normal force from the surface there. And then we're going to be saying that for body B, the rope pulls body B towards the left-hand side. So therefore, the tension is going to be towards the left-hand side for body B there. And it is worth noting that these two tension forces are of equal magnitudes, and it is clear that they are acting in opposite directions there. And they are therefore an example of Newton's third law action-reaction pairs there. And then using the same reasoning, our objects are going to be accelerating or moving towards the right-hand side. Therefore, the frictional force will still there for B oppose the motion and act towards the left-hand side there. Right. And then for our applied force, how we deal with it is that we say that our applied force acts horizontally towards the right-hand side there. Horizontally, our force acts towards the right-hand side, but vertically it acts downwards there. Horizontally towards the right-hand side and vertically downwards there. Horizontally meaning in the x direction, it acts towards the right-hand side, and then vertically in the y direction, it is acting downwards there. It is acting downwards there. So that will be Fy there, downwards there. So these are our two free body diagrams here. Now, free body diagrams tell us something that we need for our calculations. So first of all, to calculate the frictional forces, we must calculate the normal forces first. So we're going to be having for body A, you can see that the vertical forces, first we must say that our objects are not accelerating vertically. So therefore, the vertical forces must be balanced there. So for this one, we only have the normal force and the gravitational force in opposite directions. Therefore, they must be equal in magnitude there to cancel each other out there. So normal force is equal to gravitational force for body A, according to the free body diagram. And then this is going to be the mass of A being 7, G is 9,8 there. So what we're going to be having here is 7 multiplied by 9,8 there, giving us a 68.6. So the normal force is 68.6 newtons there. And then we're going to use the normal force in this equation. The kinetic frictional force is equal to the coefficient of kinetic friction multiplied by the normal force there. So the coefficient for body A is 0,4 multiplied by the normal force of 68.6 there. And then we're going to be multiplying here, and it gives us a 27.44 there. So we have 27.44 as the frictional force for body A there. Let's write that down, that the friction for this one is 27.44 there. Now let's go to body B there. Body B, we look at the free body diagram once again. Now this time it's a little bit different because there are three forces there, one acting upwards and two acting downwards, but they are balanced there, meaning the upward acting force is balanced with the two downward acting forces there. So therefore, the normal force is equal to, or it is balanced with, the gravitational force and the vertical component there. So what we have here is mg here for the gravitational force plus f sine theta for the vertical component there. So this is going to be a mass that is unknown. Let's put that in red. A mass that is unknown multiplied by 9,8 plus our applied force of 90 multiplied by sine 40 there. Now let's do a little bit of rearrangement here, and we are going to have m multiplied by 9,8 being 9,8 there. Let's keep our mass in red there, plus 90 sine 40. This gives us a 57.85 there. So what we have here is 57.85 there. So this is our normal force, and it is in terms of the mass. So moving along, we're going to say that the kinetic frictional force for B will also be equal to the coefficient multiplied by the normal force. So what we're going to have here is the coefficient of 0,2 up there, and the normal force is 9,8 m plus 57.85 there. And then to multiply here and simplify, we're going to multiply 0,2 over here and also multiply by 0,2 over there as well there. So we're going to be saying 0,2 multiplied by 9,8, 0,2 multiplied by 9,8 there. It gives us a 1,96 there. So what we're going to be having here is 1,96 multiplied to m plus 57.85 there, 0.2 multiplied by 57.85 there, and this gives us a 11.57 there. So we have here is 11.57 there. So the frictional force for body B is 1.96 m multiplied by plus 11.57 there. So let's write it down as well there. So the FK here, the frictional force here, is 1.96 multiplied to m plus 11.57 there, and that is the frictional force for body B there. So let's move along. To move along from here, we are going to choose the direction here, and our objects, we already know that they are going to accelerate to the right hand side, so we are going to be choosing to the right as positive there. So that means that to assign the direction would mean that to say that the acceleration being to the right is going to be positive over there, and then our horizontal forces there that are acting towards the right hand side are going to be positive there, and our horizontal forces that are to the left hand side are going to be negative there. Horizontally to the right is positive, but horizontally to the left is negative there. And our motion is horizontal, that's why we only focus on the horizontal dimension there. Now we assign direction so that when we come to this part, we say that the net force according to Newton's second law is equal to the mass multiplied by the acceleration. We can say there under net force, the tension that is positive minus the friction that is negative is equal to the mass multiplied by the acceleration there. So we're going to be having here, we don't have the tension yet, minus our friction is 27.44. The mass there for A is 7 multiplied by an acceleration of 2. To simplify here, 7 multiplied by 2 is simply 14. So we have tension minus 27.44 here. Transpose the 27.44 to solve for tension. So what we have here is tension is equals to 14. The 27.44 becomes positive over on this side here. So we're going to be having our tension as 14 plus 27.44 there, giving us a 41.44 there. 41.44 newtons there. So we already have the tension. So when we go to body B, what we're going to have here is, again, Newton's second law, that the net force is equal to the mass multiplied by the acceleration. What we have there is our horizontal component there, is the one that is positive, minus the tension force, minus the frictional force, those are negative, is equals to mass multiplied by acceleration there. So let's first find our horizontal component. Now our Fx is equal to the force multiplied by cos theta there. So this is going to be the 90 multiplied by cos 40 degrees. Let me write my answer down here. It's going to be 90 cos 40 degrees, giving me a 68.94 there. So I have 68.94 newtons there as my, what we have is, we have Fx minus tension minus friction equals to MA there. So we're going to have our Fx is 68.94 minus the tension we got there as 41.44 minus there our friction there would be 1.96 there, m plus 11.57 there, close bracket, is equal to our mass multiplied by the acceleration of 2 there. So m there, because this mass is unknown, and it is the same mass of this one here as well, and this is the mass of B there. And to simplify here, let us just say we have 68.94 minus 41.44, positive times negative there is negative 1.96 multiplied by m. Once again, positive multiplied by negative here is negative 11.57 there, is equal to, we have m there multiplied by that 2 there. Let me already just rearrange this one again. So we're going to be having here 2 multiplied there by m there. Now collect the like terms over here. Let's transpose the 1,96 m over to the right hand side. So what we're going to have here, we have 68.94 minus 41.44 minus 11.57. Then this gives us a 15.93. I have them 15.93 on the left hand side is equal to, on the right hand side I have 2 m. The 1,96 m goes over to that side and becomes positive, so it's plus 1,96 m there, and this will be 3,96 m, and on this side I have 15.93 there. And to solve here, divide by 3.96 here, divide by 3.96 here, and our mass is 15.93 divided by 3.96 there, giving me a 4.02 there. So what I get there is 4.02 there kilograms there. Right, let's look at this question over here with 8 kg, 15 kg blocks connected by string, and applied force unknown acting at an angle of 30 degrees to the horizontal. Frictional force for the one at the back is 9 newtons, and frictional force for the 15 kg is 12 newtons there, and it is moving at constant velocity there. Now the first thing that we're going to do here is to draw our free body diagrams so that we can just see how are our forces acting there. So for here, we're going to have, for the 8 kg, we are going to have the gravitational force, and then we are going to have the normal force, and then if you break that string over there, we have the rope pulling the 8 kg to the right, tension force from the rope, and if we are moving to the right, the friction opposes the motion to the left there. Right, and then if we go to the 15 kg, we have again a big dot, and we're going to have gravitational force acting down, and then perpendicular to the surface we have the normal force there. And then now we are going to be having the string, the rope pulling at 15 kg to the left there, and again the frictional force opposing this right motion. We're moving to the right, the friction will oppose the motion to the left, even for the 15 kg block there. And then now we have this applied force over here acting like that then, like that. However, we need to draw on the side, just have a frictional a free body diagram with the components there. So again, we for the one in the front we have gravitational force, and then we have normal force, and then we have the tension force to the left, and then we have the frictional force to the left as well. And then however, if we break that force over there into its horizontal to the right component Fx, as well as vertical Fy upwards there, and then we break it into its components there. And the next step that we take is that we say then now, because we are moving to the right there, we are going to choose to the right as positive there, and assign direction to our forces there. So focus on the horizontally acting forces. So we have this tension here to the right being positive, this friction here to the left being negative. So it means that after we write F net is equal to MA, we are going to say then tension force subtract frictional force is equal to mass multiplied by acceleration then under F net is equal to MA then. And then with this one, what we have here is that Fx, we have that Fx minus the tension force minus the frictional force is equal to the mass multiplied by the acceleration there. From that free body diagram then, before we get there, we should show there we chose to the right as positive, so the Fx is positive there to the right, the tension to the left is negative, as well as the friction to the left is negative then. And that's how from our choice of direction we chose to the right, then we assign with a positive and negative forces a direction there. And what we need to calculate is that force then, is the unknown force then. Now another piece of information that we have been given that is very important is that our objects are moving at constant velocity. That means that, what does that mean? It means if they're moving at constant velocity, the velocity is not changing. Now remember, acceleration is the rate of change of velocity. So if the velocity is not changing, that means that acceleration is 0 there. So constant velocity means that the acceleration is 0 there. An object that is at rest or moving at constant velocity has an acceleration of 0 and a net force of 0 as well there. But then at this point, we are just interested in the acceleration being 0 there. So now what we're going to be having now is, let's substitute here. So when we substitute here, we're going to have the tension minus the friction for the 8 kg is 9. The mass is 8 kg multiplied by an acceleration of 0 then. 8 times 0 gives us 0. We have tension force minus 9 is equal to 0. Now let's solve here. Transpose the 9 over to that side. It becomes positive. So the tension force here becomes 0 plus 9, which gives us 9 newtons here. Notice that with this constant velocity acceleration 0 problem, we already just get the tension. We just get the tension there. We don't have to solve for tension. We have the tension there. So that means we have the tension to substitute it over here on this equation over here. So now what is the horizontal component? The horizontal component is the force multiplied by the cos of theta there. So there we have that minus Fk there equal to Ma there. So our horizontal component is the force that we are looking for, that we want to calculate, multiplied by the cos theta. So now let's substitute them. We don't have this force multiplied by cos of theta minus the tension that we found here. It's 9. We got the tension there, and then minus 12 then. I guess one might ask then, this tension and this tension, why are they equal? Why can I substitute this 9 on this tension over here? This tension is equal here because of Newton's third law, which says that the force that the 8 kg exerts on the 15 kg is equal to the force that the 15 kg exerts on the 8 kg there, because when two objects exert a force on each other, the force is of equal magnitude but in opposite direction there. And then now the mass of 15 kg is 15 kg multiplied by an acceleration of 0 there. Right, now let's simplify here. So we're going to be having f cos 30 minus 9 minus 12. Minus 9 minus 12 gives us a negative 21. We have a negative 21 over here. It's equal to 15 times 0 is 0. Now transpose the 21 over to that side there. So we're going to be having here f multiplied by cos 30 is equal to 21 plus 0 there. Now to solve, now divide by cos 30 on the left to cancel that. We'll be left with our force. Now what we do on the left hand side, we must also do on the right hand side there. Divide by cos 30 as well on the right hand side there. And then our answer will be 21 divided by cos 30 there. It gives us a 24.25 there. We have a 24.25 Newton there force. Right. All right, with this one, we have two bodies, body A and body B, and they are in contact with each other there. So we also have the frictional force acting on A 7 newtons, on B 11 newtons. An applied force C acts also in 12 newtons, acts on A to the right hand side, also in 12 newtons. And we have an applied force D acts at an angle of 30 degrees to the horizontal to the left hand side there on body B. Now, in this one, in this question, it's not immediately clear in what direction will our objects accelerate there. And that's the first thing that we need to determine first before we start drawing free body diagrams and eventually calculating our acceleration there. So we look at this, we look at our two applied forces that are in opposite directions, and we can see that force D is acting at an angle. So we don't determine the direction of motion first. What we must do first is that we must calculate the horizontal component of force D there, so that we can compare the horizontal components there. So the horizontal component of force D, the 120, is 120 cos theta. This force multiplied by cos theta, it's 120 cos 30. It gives us a 103.92 newtons towards the left hand side there. So we can see that the 103.92 is bigger than the 75 of FC there. So that means that in a way, force D, its horizontal component, is going to in a way win, and therefore the net force is going to be towards the left hand side there. Now, according to Newton's second law, if the net force is towards the left hand side, that means that the acceleration is also going to be towards the left hand side, because it says that the object will accelerate in the direction of the net force then. Now, this is important so that we can determine the direction of friction there. So our frictional forces are going to be acting to the right-hand side there because we'll be moving to the left-hand side there. All right, now let's start drawing our free body diagram then. Now, for body A, what we have is we are going to be having the gravitational force as well as the normal force there. We have the gravitational force and the normal force, and because of the contact between the two bodies, body B will exert to the left hand side there on A. Body B will exert a force, let's call it force of B, on A towards the left hand side there. This will be B on A and A on B there, and then we're going to be having this applied force there, FC over there. And because we have already said that our objects are going to be accelerating to the left hand side, the frictional force is going to be towards the right hand side there, opposing that motion there. Free bodies are not drawn according to scale there. For body B, what we're going to have is we have the gravitational force and the normal force there. And for that applied force D, it is acting horizontally, it is acting towards the left hand side, but vertically it is acting downwards there. So that's what we have there. And for the applied force D, and body A exerts a force on body B there as they are in contact there. Body A will be exerting that force towards the right hand side there. So let's call this one the force of body A on body B there. And we have already said that our system is going to be accelerating to the left hand side. That means the friction is going to be to the right hand side there. The friction there is going to be to the right hand side also for body B as well there. Now after that, we say that we have determined our direction of motion, so we are going to choose that left hand side as positive there. Now after choosing to the left as positive, we are then going to assign direction to these forces that are acting horizontally there. So this force of B on A is to the left hand side, so it's going to be positive, and the FC to the right is going to be negative, and the frictional force to the right is going to be negative there. The force of A and B to the left is positive there, and the horizontal component there, Fx, is to the left, so it's going to be positive. The force of A on B is to the right, is going to be negative. The frictional force is also going to be negative over there, as it is also to the right hand side there. So our focus will be the force of B, A, and AB. We know that from Newton's third law that they are equal in magnitudes there. So that means that we are going to be substituting one into the other there. All right. So we have the net force, F net equals 2ma, and according to our free body diagram here, we have on the positive side we have the force of B on A minus force C minus frictional force equal to ma there. And then for this one here, for body B, what we have is we have Fx there minus the force of A on B minus the frictional force there is equal to ma there. And then next we are going to substitute what we have. So what we have here, so we don't have the force of A on B, of course. So we have the force BA minus FC is 75 minus 7 is equal to our mass of 9 multiplied by 8 there. And let's simplify a little bit there. So we said that we're going to have negative 75 minus 7 there is going to give us a negative 82 here is equal to 9a. So let's make the force of B on A the subject of the formula. Let's transpose the 82 over to that side. So we're going to be having the force of B on A equal to 9a. It comes over to the side and becomes positive 82, and then we're going to call this equation number 1 there. And then on this side, what we have here is we have that Fx as 103.92 minus the force of A on B that we do not have, minus the frictional force of 11 is equal to a mass of 14 multiplied to A that we also do not have there. So let's simplify a little bit over here. So we have 103.92 minus 11 there, giving us a 92.92. So simplifying here a little bit, we have 92.92 minus the force of A on B is equal to 14A there. And then let's call this one equation 2 there. Let's call this one equation 2 there. And then what we're going to do next is that we are going to be substituting equation 1 into equation 2, because the force of B on A is equal to the force of A on B there. So we see the force of A on B, we're going to be putting the 9A plus 82 there. So let's have that. So we're going to be having 92.92 minus 9A plus 82 there is equal to 14A there. So let's simplify here. We're going to be having 92.92 positive multiplied by negative there is negative 9A, positive multiplied by negative again is going to be negative there, 82 is equal to 14A there. So now it's a matter of collecting the like terms. So we're going to be transposing the 9A over to that side there. We're going to be left with 92.92 minus 82 over on the left hand side, and on the right hand side over there we're going to be having the 14A. The 9A comes over on this side, it becomes a positive there, 9A there. 14 plus 9 gives us a 23A there, and then 92.92 minus 82 is going to give us 10.92 there. And to solve for acceleration here, we're going to divide by 23 here and divide by 23 over on this side there. And this is going to cancel out, and our acceleration there is going to be, so we have 10.92 divided by 23 there, giving us a 0.47 there. So we have 0.47 meters per second squared. We chose the left as positive. Our positive answer therefore is to the left hand side there. And if the question requires you to calculate the force that B exerts on A and A on B, you simply substitute your acceleration into equation 1 there, as you would be solving for tension in that tension problem there. All right.